Okay, so let's look at another example, a different delta H situation. So remember, delta H is just the heat given off or taken in depending on what we're doing. And this particular example focuses on delta H of condensation. So if something condenses, that would be listed in the problem here, for example, that will deal with delta H of condensation. And basically what we're doing is we're going from something as a gas and we turn it into a liquid. If I'm doing the reverse of this, or the opposite, that would mean I'm going from liquid to gas. And liquid to gas, that phase change was when I vaporize something. So that delta H value was the delta H for vaporization. Remember, these two numbers are the same, the number value itself. But one reaction goes from liquid to gas, the other goes from gas to liquid. So the reactions are opposites of each other or reverses of each other. So the reverse of any thermochemical reaction, a reaction again where you're representing heat being released or heat being taken in, the opposite or reverse is always negative. Okay, that value. And that's what we looked at in a few slides ago. These are the same number, but this is negative. Okay, so as long as I can find this number, I just make it negative and I get this one. And that's what I need for this problem. So for us, we take a look. The delta H of vaporization for this particular compound here that's in the problem is 35.2 kilojoules. So the reverse reaction, condensing, is just the negative of that number, negative 35.2. So the math part kind of works out the same here. If we take the problem, I have 42.5 grams of CH3OH. This compound is also called methane. Condenses from gas to liquid. So if it condenses, I know I'm doing the reverse, so I have this number. And I'm starting with 42.5 grams. And just like the last problem, we want to get that into moles. So 1 mole of CH3OH, molar mass on the bottom, that will be roughly 32 grams. And then I just need to compensate for the heat that I have. So in this case, I have negative 35.2 kilojoules of heat given off for every mole. So right now I want heat and moles are on the top. So moles will go on the bottom. And this number will go on the top, kilojoules. So to solve this, we multiply across the top and divide by the numbers that are on the bottom, keeping in mind that this is negative. So overall, my answer should be negative. And if I'm condensing, I should be giving off heat, or giving off energy in the form of heat. So I should get a negative number. So let's go ahead and type these in. 42.5 times my negative 35.2 divided by 32. And again, this should be negative. I just didn't type in the negative number on this calculator, but my overall answer will be negative 46.75 kilojoules. So that's how much heat is given off from this amount of methane turning from a gas to a liquid. And if we look at it, gram-wise, I have more than a mole. 1 mole is 32 grams. I have 42. So my heat then should also be a bit more since I have more of this substance. More of the substance means more bonds breaking, forming, all of that stuff. So the heat gets kind of messed up with that too. So I should have more heat produced. All right, let's go ahead and look at the next example. This is the last one. And this is kind of a reverse. So what information do we need for this? We still need to make sure we know the delta H of whatever situation I have, combusting, vaporizing, freezing, any of that stuff. And I also need to make sure I have either the grams of something, or in this case I'm going the other way. They give me the heat that I'm giving off. So what do we need? Well, we need to make sure we know the delta H. So here's how we have to think about this. it says what mass of methane. Now, some of my delta H values, depending on the situation, can be negative. So if we look at this problem, it says I'm burning something. Burning meant combustion. Combustion meant I'm giving off heat. If I'm giving off heat, my delta H value is negative. So in this case, if I'm finding mass, I can't really get a negative number for mass. So when we have our delta H value, we'll make that positive, so it will match the heat value that I have, or we'll either make it negative, so it will match whatever value is here. So for example, if I have 12,880 kilojoules of heat that's being given off, I just need to make this number down here, the signs match, basically. So either they're both positive or both negative, so the negatives cancel out, ultimately giving me a positive number for mass, because I can't have a negative amount of grams. It doesn't really make sense. So another way that this equation could look like, instead of giving you kind of the delta H value, they could give you the equation. So here's the equation for methane being burned, and for us, we know this is exothermic, or giving off heat. So that could be shown on the product side of your reaction, so plus 726, okay? So let's go ahead and take a look. Here I know I'm starting with 12,880 kilojoules of heat. And my delta H value, I'm going to make mine positive, so the signs match. And my delta H value for methane combusting is 726. So if I'm starting with heat and I want to get to grams, the first thing I can do, this value again relates how many moles, or how much heat is given off for 1 mole. So if kilojoules is on the top here, it's got to cancel, and I'll put that on the bottom. So 726 per 1 mole of methane, CH3OH. Then I just need to switch this to grams. So if I have moles of this stuff, I just have to get to grams, which means this time, instead of dividing by molar mass, I want the grams, so they're going to go on top. So my 32 grams, my molar mass of CH3OH for every 1 mole. Okay. And then, so here I will multiply across the top, divide by what's on the bottom, that will give me grams. And if we think about it, I should get a lot of grams because I have a lot of heat. And this tells me this is only 1 mole of this stuff, and I have like 12,000 kilojoules of heat. So I should get a lot of grams because there's a lot of heat being given off. So when we multiply this, we'll take our 12,880 times 32 across the top, divided by 726. And that will give me 576 grams of the methane that I would need. Now, that's a decent amount. That should be a whole lot more than what's in 1 mole, because this is tons of heat. So this would be kind of a reverse idea of starting with heat, ending up with grams, instead of starting with grams and ending up with heat. Okay, so this is how many grams of methane I would have to burn in order to give off this much heat. That's a lot of heat. Now, this is the last example for this section. You have a worksheet to do, and the sub will pass that out, and that's all you have to worry about for the rest of class today. So go ahead and give it a shot. If you need to replay any parts of the video, that's fine. If you've got questions, we'll go and cover it tomorrow. Just go ahead and try some of the problems and see what you can come up with, and we'll go over it tomorrow in class.